Welcome to this explainer. Today, we're going to take something that looks like a completely mundane, messy, everyday construction task and totally reframe it. We are revealing the act of pouring concrete for what it truly is, an incredibly high-stakes, time-bound operational and chemical challenge. In fact, if you're an information engineer, consider this a masterclass in time-bound operational management. Let's get right into it. I want you to picture a towering skyscraper under construction. You've got millions of dollars on the line, dozens of crew members standing by, crane schedules mapped out to the absolute minute. Now, ask yourself, what happens when a single delivery truck gets delayed in traffic? In most industries, a delay is just an inconvenience. But in the concrete industry, a delay of just a few minutes can literally compromise the structural integrity of an entire building. To understand exactly why it's so critical, we've got to bust a massive myth right out of the gate. You'll hear people all the time say they're waiting for concrete to dry. Actually, scratch that, concrete doesn't dry, it cures. The exact second water hits the cement powder, an unstoppable, almost biological-like chemical reaction kicks off called hydration. It has absolutely nothing to do with water evaporating. It's about molecules actively bonding together. And once that reaction starts, the clock is ticking. Okay, so what happens if that hydration process gets interrupted? Say a truck gets stuck in gridlock and the concrete that's already sitting in a column begins to set before the next batch even arrives. Well, you get what engineers call a cold joint. This is a severe structural defect. It's essentially a seam where the old concrete and the new concrete simply refuse to chemically bond. So instead of a solid, single monolithic pillar, you've effectively built a crack right into the structure. Under lateral loads, think heavy wind or an earthquake, this weak interface completely ruins the column's shear resistance. It's a catastrophic failure waiting to happen. To prevent that disastrous cold joint from happening, the entire construction industry is forced to operate under one incredibly stressful, immovable constraint: the 90-minute ticking clock. Right from the very moment water hits cement at the batch plants, ASTM standards dictate that you have precisely 90 minutes. That's 90 minutes to deliver, place, and finish the pour. That is a razor-thin window for the entire logistics chain to do its job perfectly. If you miss that window by even a little bit, the material starts turning solid and is completely unusable. It literally just becomes garbage that has to be thrown away. This strict perishability totally changes the game. That transit mixer you see rolling down the highway, it's not just a delivery truck. It is, in reality, a mobile, powered-on chemical reactor racing against time. The driver isn't just moving a product from point A to point B. They are actively managing a volatile chemical state in transit. So, how in the world do engineers fight this ticking clock when temperatures spike and traffic stalls? It all comes down to slump and chemical admixtures. As concrete hydrates inside that spinning drum, it loses what engineers call slump. Slump is basically a measurement of the consistency of the fresh concrete, essentially how much the wet concrete sags under its own weight. It tells you how workable it is. But here's the really critical catch. When the concrete gets too stiff, you absolutely cannot just dump more water in there to make it flow again. Adding water drastically decreases the final structural strength and makes it more permeable. So, if you can't add water, what do? This is where we get to see molecular chemistry on demand. Instead of water, plants pump in super plasticizers, specifically polycarboxylate ethers, or PCEs. These molecules do two pretty amazing things. First, through electrostatic repulsion, they give the cement particles similar electrical charges so they physically push away from each other, which releases trapped water. Second, through steric hindrance, they use these long polymer chains that act like microscopic brushes to physically block the cement particles from clumping back together. The result? You get highly workable, freely flowing concrete without adding a single extra drop of water. These chemical retarders are essentially a giant pause button. They save the load from hardening inside the drum, while perfectly maintaining that crucial water-cement ratio you need for maximum strength. By tweaking this chemistry, producers can safely extend workability. In some extreme cases, like super remote areas where transport takes hours, specialized hydration control admixtures can literally keep the mix fresh for up to 3 whole days without losing quality. No way, right? Now, while all that perfectly calibrated molecular magic is happening inside the drum, let's zoom out to the system level and look at the logistics side of things. Welcome to the dispatcher Tetris game. This brings us right to the Q problem. Think of the concrete plant as a massive buffer between the raw bulk materials, your sand and gravel, and the actual demand of the construction site.
You've got wet mix plants that mix everything centrally for highly consistent continuous output, and dry mix plants that rely on the truck to mix everything in transit. But regardless of the setup, if this buffer fails and the plant runs out of just one ingredient, the entire construction site grinds to a halt. We're talking thousands of dollars bleeding out in idle labor, not to mention risking those dreaded cold joints.
And a person navigating all this absolute chaos? The dispatcher. The dispatcher is really the unsung hero of the whole construction world. They are essentially playing a high-stakes, real-time game of Tetris. They have to perfectly balance batching times, precise chemical dosages, unpredictable traffic patterns, and the site's pour rates. It's totally normal for them to handle up to 20 last-minute order changes per pour. Send tricks too fast, they idle on site and the concrete starts setting. Send them too slow, the site runs dry, and boom, you've got a cold joint. Because it's so complex, human intuition alone just doesn't cut it anymore. By plugging into specialized algorithmic logistics software that tracks vehicle data and site demands in real time, dispatchers can radically optimize this massive flow. This tech can literally slash overall operational costs by up to 15% and boost the number of delivered loads per vehicle by 20%. It takes a ton of stress right out of the system. So let's look at how this brilliant combo of molecular chemistry and algorithmic logistics is actually pushing the industry forward in our final section, extending the pouring window. Remember that rigid 90-minute rule we talked about earlier? Well, thanks to wild traffic congestion and urban sprawl, that rule forces plants to throw away roughly 3% of all the concrete they produce. That is a massive amount of environmental and financial waste. So the New Jersey Institute of Technology, NJIT, stepped in with a major study. They wanted to know, could modern chemical admixtures safely stretch that 90-minute window all the way out to 150 minutes without hurting the concrete's structural integrity? The findings they came back with were brilliant. As you can see from how they tracked air content over time, using extended set retarding admixtures allowed the concrete to hold on to its required air content way past the 90-minute mark, even hitting that 150-minute deadline. Both the fly ash and slag mixtures stayed totally workable and perfectly within spec. And it gets better. The temperature data proved that the internal environment of our mobile reactor remained completely stable. Across the full 2.5 hours, for both slag and fly ash mixtures, the temperature never spiked. The chemical retarders did their job perfectly. They paused the heat-generating hydration process, keeping the whole mix cool and viable despite the massive delay. The takeaway here is huge. The NJIT data proves definitively that the current 90-minute limits are actually highly conservative. The test cylinders they poured at 150 minutes still smashed right through their 6,000 psi compressive strength targets, and they showed zero negative impact on freeze-thaw durability. It just goes to show that with precise time-bound operational management and on-demand chemistry, we can safely extend that ticking clock, saving millions in wasted material and idle labor. I really hope this explainer has completely changed how you view construction logistics. What looks from the outside like a dirty, simple mix of sand, water, and cement is actually this delicate, high-wire dance of molecular science, algorithm-driven dispatching, and intense supply chain management. It should definitely leave you with a profound appreciation for the high-stakes chemistry rolling down the highway right next to you. Think about all of that the next time you're stuck in traffic next to one of those spinning drums.